If you're building machine learning models for Alzheimer's research, the Alzheimer's Disease Neuroimaging Initiative, or ADNI for short, is arguably your most important resource. But there is a bit of an open secret in biomedical AI. Pre-processing ADNI tabular data is an absolute minefield. So in this explainer, we're going to break down a highly practical, real-world pre-processing pipeline. We're going to take raw, messy clinical records and engineer them into a clean, leakage-free dataset that's completely ready for robust machine learning.
We have to start with a massive trap that catches countless data scientists. The raw ADNI dataset contains 16,421 observations. Now, it's incredibly tempting to feed all of those rows straight into your algorithm, right? But here's the catch. Those aren't unique people. They're longitudinal visits representing just 2,430 unique patients. If you treat those visits as independent samples, you're creating massive data leakage. Your model will literally see the exact same patient in both the training and testing sets. That gives you the illusion of a perfect, highly accurate model that will immediately fail the second you test it in the real world.
Fixing that leakage is exactly what we're going to conquer today. By the way, if you're building healthcare AI or working with complex clinical data, you might want to hit subscribe right now so you don't miss any of our advanced pipeline breakdowns.
Okay, let's dive into our blueprint. We're using a 4-step data assembly line. Step 1 is feature triage. Step 2 is the time machine. Step 3 is the repair shop. And Step 4 is assembling the final dataset.
Station 1, feature triage, where we filter down our 116 variables.
The original data is practically a goldmine, spanning 9 conceptual groups. We've got everything from basic demographics, like age and education, to cognitive assessments, structural MRI parameters, high-tech PET imaging, and cerebrospinal fluid biomarkers. But there's also a ton of administrative noise in there, like device technical specs and redundant patient ID columns.
To clean this up, we immediately drop those administrative identifiers and duplicate columns. But then we have to make a tough real-world decision. We actually drop the PET scan data. Why would we do that? Well, despite its theoretical value, PET scans come with a very high clinical cost, limited real-world access, and high rates of missing data. Plus, neuroscience experts generally agree that relying on them limits the utility of a standard screening model. By focusing purely on data he'd access in a routine clinical setting, we successfully cut our variables down from 116 to a lean, highly relevant 46.
Moving right along to Station 2, the time machine, transforming our data from longitudinal to cross-sectional. This is absolutely crucial. Most standard machine learning algorithms, like random forests, support vector machines, or TabNet, assume your data is cross-sectional. They expect each row to be an entirely independent sample. The wrong way to handle ADNI data is treating every patient visit over several years as an independent overlapping sample. The right way? We have to translate those longitudinal records into a clean, cross-sectional dataset. We do this by collapsing a patient's entire history into a single, highly reliable snapshot. So, how exactly do we build that snapshot? Well, for fixed demographics, we simply grab the baseline value recorded at their very first visit. For continuous numerical variables, like cognitive test scores or MRI volumes, we calculate the median across all of their visits. Using the median is a great trick because it provides incredible inherent resistance to clinical outliers. Finally, for the target variable, which is the patient's diagnosis, we take their last recorded diagnosis to represent their final clinical status. Of course, while traversing this time machine, you've got to watch out for clinical data quirks. For instance, in the ADNI dataset, we found 3 variables tied to the RAVLT memory test that actually contain negative scores. Clinically speaking, a negative score on these specific tests is logically impossible. But instead of just deleting these entire patient records and losing all that valuable data, we isolated these 58 anomalies and replaced them with NaN. This effectively marks them as missing data to be handled in our next step. And that leads us straight into Station 3, the repair shop, where we systematically handle missing data and outliers. Think about this for a second. How do you handle a vital clinical feature, like a CSF biomarker, when 48.35% of the data is just completely missing? Or what about the digit score cognitive test, which is missing over 66% of the time?
You have to strike a balance between preserving information and controlling noise. After testing a few different thresholds, we established a strict rule of thumb. We drop any feature with more than 40% missing data. So right off the bat, the heavily absent CSF biomarkers and the digit score test are out. For the remaining features, the ones with less than 40% missing data, we use intelligent random forest imputation to predict and fill in the blanks based on the patient's other clinical features.
Actually, imputation is a massive topic in biomedical AI, so I'm curious. Let us know down in the comments what imputation methods you prefer when you're working with messy clinical records. Are you team random forest, k-nearest neighbors, or do you use something else entirely?
Listen, if you take nothing else away from this explainer today, let it be this absolute golden rule. Whether you're using random forest for missing data or an isolation forest to find outliers, you must strictly fit these models on the training set only. You calculate your medians and fit your algorithms on the training data, and then you apply those rules to your validation and test sets. If you let your imputation models see the whole dataset beforehand, you're literally leaking future data right back into your pipeline.
To manage outliers without triggering that data leakage, we fit an isolation forest on our training data. It found 73 highly abnormal patients, which is about 3% of our dataset, with over 90% of those outliers belonging to the Alzheimer's group. We temporarily set those outliers aside, calculated the training set median for each feature, and then used that median to replace the wild outliers across all sets. Finally, we apply adaptive scaling. We don't just blindly use one scalar for everything. We test the distribution of every single feature. If it's normally distributed, we use standard scalar. If it's heavily skewed, we use robust scalar. And if neither applies, we fall back to min-max scalar.
Finally, we arrive at Station 4, the final product, and achieving binary target clarity.
In ADNI, patients generally fall into three camps: cognitively normal, mild cognitive impairment, and Alzheimer's disease. To establish a really reliable clinical screening baseline, we temporarily drop the 779 patients in the highly heterogeneous MCI group. By focusing purely on a clear binary classification, cognitively normal versus Alzheimer's disease, we make our model boundaries incredibly distinct. This is perfect for a primary screening tool, and honestly, it's excellent for educational clarity. After dropping those MCI patients and safely removing patient ID columns to prevent any bias, look at the numbers we're left with. We have 1,651 independent patients. 835 are cognitively normal, and 816 have Alzheimer's disease. That is a perfectly independent, brilliantly balanced dataset, a 1.02 to 1 ratio, completely ready for fair, unbiased machine learning training. Now, even though we used a binary target today to make the pipeline architecture crystal clear, keep in mind that this exact preprocessing pipeline is incredibly adaptable. You can easily reintroduce the MCI group later for complex multi-class classification. Or you could adapt this exact cross-sectional strategy to predict disease progression and MCI conversion over time.
So, this leaves us with a critical question to constantly ask ourselves going forward. Are your models actually learning clinical patterns, or are they just memorizing leaked, overlapping data? By actively translating longitudinal records into isolated snapshots, intelligently handling missing values, and strictly isolating your training sets, you guarantee that your model's intelligence is real.
If this explainer helped clear up the ADNI tabular data minefield for you, please drop a like, hit subscribe, and share it with your lab mates and fellow data scientists. Keep building robust models, and we'll catch you in the next explainer.